whatever your language is for that. Right, but that's, what is that? This is dt of f of zeta of t, right? Which is equal to, by assumption, big F of zeta of t. So you see that this is just equal to the integral from t0 to t1 of big F of zeta of t dt, which is the kind of integral I started with today. It's a real integral of an a-valued function. And, oh, I'm sorry. I somehow have, I'm an idiot. That's not right. What am I doing? What am I doing? Yeah, I'm sorry. I just oh, I'm an idiot. This right here, right? This piece right here is the df, right? F is equal to the derivative of big F, and then so that we have that times d zeta dt, which is what? That's d dt of f of big F of zeta of t, right? Chain rule. Which then, I'm sorry. So so then I've got the integral from t0 to t1 of big df dt of zeta of t, right? Which is equal to f of, my notation is slightly off here. That's supposed to be d dt of f of zeta of t, right? d dt of f of zeta of t, which is then f of zeta of t1 minus f of zeta of t0, also known as f of q minus f of p, which is what I set out to prove. What's next in the theory of integration? What do you do next in calculus 3? Once you have an integral, line integral, and then you've defined basically, your fundamental theorem of line integrals, right? Usually, the next thing I do is start talking about topology of line integrals. So, C1 f times d zeta equals integral over C2 of f times d zeta. The integral over C of f times d zeta equal to 0, and f has antiderivative. Df d zeta equal to little f. Now, I'm being intentionally vague. So this is all in context, right? This is on U, right? And here I'm assuming that U is some simply connected subset of A, right? So what's the theorem really? Following our equivalent, right? I'm still being a little bit vague. So here C1 and C2 are two curves which have matching terminal points, right? So the picture for 1, 2, and 3. For 1, the picture is basically, and here's the universe, U, right? For any coterminal paths, we get the same integral. 2, of course, that C is a loop. So for all loops in U, we integrate to 0. And 3 is what it sounds like. You know, we have to be able to basically build. You pick a base point Z naught, and to get over here to Z, actually you basically go here and then approach it like that, this way, and then by path independence, you can approach it this way and then go like that. And so you're going to be able to define f of z as something like the integral from z naught to z of f of zeta d zeta. That's the usual potential energy construction, except done over the A calculus. If you assume path independence, you can imagine approaching that point, straightening it along just one direction, the other direction, and then you can vary along those. It's the usual argument we give to prove that the partial derivatives of this function, in fact, match the necessary things for the conservative. It's the conservative vector field potential energy construction in calculus 3. That's not really a two-dimensional. It's not really a three-dimensional. It's an n-dimensional idea. You can do it. Of course, I think you guys. This is even easier, right? I mean, if you can do it for arbitrary C1 and C2, you can take any loop and break it into a C1 and C2, right, by reversing the order. This is an oriented integral, right, in the sense that this is equal to minus the integral of minus C of f of zeta d zeta, right? It's a line integral, right? All right. Now, let me. There is more to show. There is more to show, and this is one of the places where this paper could be improved by being a little bit more detailed. The proof of 3, you actually, when you get into it, and actually do need the Cauchy-Riemann equations to make this go through. I have some of those details in equations like 150 and 151 in the paper. So next up, but I don't think it's appreciably different than calculus 3. I mean, really, this is just the usual calculus 3. I call these the topological theorems. In some sense, these are topological theorems for the line integral. I mean, this is where topology meets analysis, though, isn't it? Part 3. It's part of the reason topology has more applications than you might at first think. I think we sometimes forget that topology did not arise from pure mathematics. It actually arose from applied math in a way which I think we've sometimes forgotten. Anyway. Although the French might disagree. All right, so theorem, this is my theorem 1010. We have f from U to A. U is simply connected. What's that mean? I'm going to assume that f is continuously. I mean, to really define simply connected, it's tough. I mean, that's a topological term. It basically, for us, means there's no holes, there's no things to get stuck on. You can deform things continuously to a point. Anyway, f is continuously differentiable in the real Fréchet sense. All right. Then the A-valued 1 form f times d zeta, all right, is exact if and only if f is a differentiable. So what do I mean by exact? So exact and closed, right? What is exact? Eta equals to d gamma means beta exact, right? If it can be written as the differential of another form. And I'm suggesting, without a lot of background, this is another thing that's missing from my paper, is really a complete exposition of algebra valued differential forms, but I'm assuming that you can take basically the dx's, the dy's, the dz's, and just put algebra coefficients next to them, and it still makes sense. For example, if I asked you to multiply dx plus 3i dy, take the wedge product of that of 3 plus I dx, well, 3 plus I parentheses, dx, you guys wouldn't bat an eyelash. You'd immediately tell me, well, dx wedge dx is 0, and that's going to give me 3i times 3 plus I dy wedge dx, right? And so that's, minus 9, I'm sorry. Minus, I can't do math, 9i minus 3 dy wedge dx, right? You guys would do that kind of calculation without, if I asked, even if I didn't tell you define it, I didn't define it, did I? We just did it. So what I'm saying is just the natural outgrowth of algebra multiplication combined with differential forms, which we could define carefully, but I admittedly have not. I don't think it's going to get us into much trouble, though. So let's go this way. Suppose that f times d zeta is exact. What's that mean? This is equal to the differential of what? Something. Let's call it phi. My goal is to show that f is a differentiable, right? So this is what? Now here, this should be something like d sum of vi, right? So by definition that I have not stated, but we all know, this is d phi vi. In other words, the differentiation just happens on the coefficients of the form, and the v rides along. What's this? I'm assuming that would be something like the sum over u, I, v, I, right? For the components of f times sum over j, I guess, 1 to n of what? This is dxj vj, right? This is given. Nah. And so from this perspective, it's kind of tough, right? Kind of tough to go forward here. So what I'm going to use is simply connected, right? Simply connected means I can use Poincaré's lemma. What's Poincaré's lemma say? On simply connected set, in this case, we can view it topologically as a subset of Rn, right? So Poincaré's lemma says that there's a connection between closed forms and exact forms. So it suffices, in fact, to show it's closed that will imply the existence of the exact thing. it's much easier to show it's closed. To show it's closed, so if I can show that f times d zeta closed, that will imply exact by Poincare. And yes, I haven't proved Poincare's lemma for algebra valued forms either, but I think it's relatively apparent that you can bootstrap it up to algebra valued forms by simply using the regular Poincare lemma component-wise and stringing them together. To show this is closed, though, is a joy, because all I have to show is that the differential of f times d zeta is equal to 0. And so this is I'm going to do it formally. But I give details to basically show that the following formal calculation is not utter nonsense. It's in fact legit. What's df? df is nothing more than partial f partial zeta d zeta. And yes, d zeta wedge d zeta is 0. Now, I show that in much more detail in the paper, which I'll project because, well, I don't want to keep you guys here all day. Hey, well, I already finished that, didn't I? Sorry we missed last Wednesday. I feel bad about that. But I felt worse on that day. Let's see here. Come on. Where's that stupid thing? Maybe it says. It is that. Oh, good. Come on. So here's the calculation I was talking about. I can find my laser. We'll get through this section and call it a day. So here's the proof that d zeta wedge d zeta with the natural definitions I never wrote down, but assumed everyone knows are true. So this wedge that, assuming uses the distributive properties, you end up with wedges upon wedges upon wedges. And the thing is that either they're equal, so that just drops out, right? I equals j means that this wedge product's gone. And over here, I can rewrite these as to make I less than j for both. And when I do that, because I'm assuming commutative algebra here, this is where I need commutative, right here. These actually end up being minus each other, and so they cancel out. And then the straight calculation of this without just relying on notation, as I did on the board, well, df is that's the total differential of f, right? These, by the way, are algebra. This is like an algebra valued partial derivative. This is algebra valued. That's algebra valued. But the point is, then that what do I do here? What happened right here? You notice that the partial derivatives with respect to 1, 2 dot n all change to 1, 1, 1, 1, 1. I'm using Cauchy-Riemann equations. And I then look at it, I just pull out the partial 1f. And what I'm left with is dx1 plus v2 dx2 plus vn dxn, which is, of course, the zeta, the d zeta I was encouraging us to think of as its own thing. It is its own thing. It's a differential algebra valued one form. That's what it is. And as you can see, its wedge product is 0. By Poincare's lemma, then f is, in fact, exact. So d phi is equal to f d star. And so there you go. I seem to have not stated it. Maybe I stated it as an if-then in the theorem. I don't know. Where's the other direction of the proof here? Maybe it's obvious. Oh, in fact, the calculation pretty much shows you that the other way goes around, right? Well, I mean, you can see from what we just did that if A is differentiable, the form is closed. So consequently, it's exact, right? So I think, which way did I go here? I'm sorry, I've lost track. I assumed it was exact to prove it was closed. What? I think I've gotten confused here, guys. What I just showed you was a proof that if f is a differentiable, it implies it's closed and hence exact, right? To go the other direction, I'm an idiot. I'm so sorry. To go the other direction, I should show what? I should show that the Cauchy-Riemann equations hold, right? So if it's exact, that implies it's closed. The fact that it's closed, I think, implies the Cauchy-Riemann equations when you look at that. Then finally, the corollary, if we have simply connected, if we have a simply connected set such that the integral is 0 for all loops in C, that's true if and only if f is a differentiable on U. So this is the algebra analog of Cauchy's integral theorem. Cauchy's integral theorem says that if you have the integral of the complex integral around loops in a simply connected set, then that implies that the function that you're integrating is in fact complex differentiable. Well, anyway, so suppose it's 0 for all loops. That means that there exists a antiderivative, like so. And on the other hand, I can calculate df as this, which is that, which is that, which is that. So that shows that f star d zeta is exact because it's the differential of f. So then the corollary follows from the previous theorem I just stated. So the usual proof of Cauchy's integral theorem does not involve, I don't think it involves the potential energy argument. Like, I think the usual proof is a little bit different. It's, well, it depends on how picky you want to be. There's two proofs of Cauchy's integral. There's the proof of Cauchy's integral theorem, which is built over Green's theorem, and the assumption that you already have continuity. So you can apply the Green's theorem, and it's like 2 lines. The other version requires more nuanced arguments and so forth. But anyway, I just want to get through it here for the moment. This is the kind of weird thing is this result here. So I have a zeta as an arbitrary point in an open simply connected subset of A of the algebra, and so C is going from some point zeta not to zeta where it's a variable endpoint. So it makes sense to differentiate that, and if you do that, you get f of zeta. So this is the algebra analog of the fundamental theorem of calculus part 1. Kind of funny, it comes at the end of everything, right? In like calculus, we prove it at the start, typically. Here, I end up using all of my other bells and whistles to prove the fundamental theorem of calculus part 1. But that's kind of important because then you could use that to define the logarithm using an integral. And you could study properties of the log in view of this integral. In the same way we could define logs in calculus 1 in terms of an integral. That's most of the reason that this theorem is important to me, is its relation to showing, I mean, you know, if you differentiate this with respect to zeta, you get 1 over zeta, right? Which shows you the derivative of this function is 1 over the reciprocal function, which shows you that's what we want for the log in particular. I mean, among other things, we want it to be the inverse of the exponential, of course, but you can prove that it's the inverse for the exponential without assuming that. You can, anyway. Well, guys, it's been a long day. I appreciate your patience with me. I think that's a pretty good place to stop. I'm sorry if I've glossed anything over this section. You can hit the stop record button.